Hi everybody, welcome to another video in Precalculus section 4.4 Logarithmic functions. Logarithmic function with base a. The base a here is defined similarly to exponential function that is being positive and not equal to 1. And it is denoted by y equal to log base a of x. And we said y is the logarithm with base a of x, and we define like this: y equal to log base a of x if and only if x equal to a to the y power. Right. First of all, the way we write the log, the base a is the subscript, so we should write the log. The base a is the subscript and then x, so it should be like this. And the logarithmic form y equal log base a of x and x equal to a to the y. Right, so what we see here is in both logarithmic form and exponential form, a is the base greater than 0, not equal to 1. And the reason we need to do that, so what we see here is both of them, the base a will stay the same, the equal sign will stay the same. What we do, we just switch in the x and the y, so the x will be on this side and y on the other side. So since we switch in x and y, what we have here is an inverse function. So in that case, we can say logarithmic function is the inverse function of the corresponding exponential function. Right, now we did mention that the exponential function y equal to a to x, we need a to be positive, because if a is negative, when we have negative 1 to the 1/2, by the way, if the base is negative 1, equivalent to the power 1/2 is equivalent to square root, and when we have this, it is imaginary. So the base must be positive, so we do not encounter any of imaginary. So because of that, a is positive. Next, y a has to be different than 1. If a is equal to 1, then we just have 1 to the x power, which is just x. I mean just 1. In that case, it's not exponential function. It is a constant function. So we want the base to be positive, so we don't have to encounter any imaginary numbers. And we want it to be different than 1, so we don't have to enter any constant. And by the way, the graph of exponential function could be that when a is bigger than 1 and the other way around. If a is between 0 and 1. Either case, it is one-to-one function, because the horizontal line test only cut the graph at one point. So because it is a one-to-one function, there will be an inverse, and the inverse will be y log base a of x. Right. So what we do is the base a will stay the same, the equal sign will stay, and then we switch x and y. That's where we go from exponential function to logarithmic function. Right. Now, see how it works. Convert the following to logarithmic form. So what we have here is the base 2. For the exponential form, we will write log base 2. 2 is a subscript for logarithmic form. And after that, we just switch the 32 and the 5. So it will be just like that. Similarly here, the base is a, so we write log base a. And then 5 and 7, we swap. Here, our base is 3, so we say log base 3. And then we swap the other two numbers. Yeah. So the base will be the same, except in the logarithmic form, the base is the subscript, whereas the exponential form, we have the base on the same level. So we just need to write that proper form. Right, now log base 2, so the base is 2. If we change to exponential form, we have 2, and then 4 and 6. 4 and 16 we interchange, so that's what we have. Now, we'll go back to what actually a logarithmic function means. So, of course, when we say a log base a of x, we mean a to what powers is equal to x. Right. So when we write log base 2 of 16 equal to 4, if we don't have equal to, log base 2 of 16, what's that equal to? Right. That will be the same question as 2 to what powers is equal to 16. That is the same question as that. And whatever that is, will give us an exponent. So 2 to what exponent is equal to 16? The answer to that question is equal to the log. So we see 2 to what power is equal to 16? The answer is 4. So 2 to the 4 is equal to 16. So that's what the log means. Right, same thing here. A to what power is equal to 5? Well, we have a, so we cannot really say that, but the base is 5, and swap the other two number. The 3 will be here, and the 5 will be here. It's just different in the log. The base is the subscript on the exponential form. The base on the same level as everything else. Now the 3 is the subscript, which is the base. In exponential form will be in the same level, and then we interchange the other two. X and 2.3. Right. So that's what we have. Right. So the base will stay the same, and then we just interchange the other two. Right. Now evaluate the following logarithms. Log base 3 of 27. What's that equal to? Whatever it is equal to, the question will be similar to 3 to what power is equal to 27. Right, so we try to answer that question. So we say 3 to what power is equal to 27. That's the same thing as keeping the base 3 and swapping the 27 and x. Now, 3x 27 is 3 cubed. We write like that, so two things are equal. The bases are equal, the exponent will be equal. So we have x equal to 3. Now, similarly, we make this equal to x, and we say the base 25, and then we swap the other two, x and 5. We say 25 to what power is equal to 5, and we try to answer that question. Right, now 25 we can write as 5 squared, and 5 is 5 to the first power. We're trying to write like that, so I have the same base. When I have the same bases, the exponent will be the same. So here, 5 to the second and then to the x, we will multiply this power 2x equal to 5 to the first, and 2x equal to 1, so x equal to 1/2, right? 2x equal to 1, so x equal to 1/2. Right, so 25 to the 1/2 is equal to x. 25 to the 1/2 is equal to 5. Right, 25 to the 1/2 is equal to 5. So this is equal to, we can just say it. Yeah. Right, next, blocks base 4 of 1/2. We don't know what it is, so we make that equal to x, and then we write 4 to that power is equal to 1/2. Now 4 is 2 square, because 4 and 2 both of them have base 2. Here 2 to the first power is 2. Now move 2 to the first power from the bottom to the top, cross the line, change the sign, and now we multiply the exponents here. Now two things are equal, the bases are equal, the exponent will be equal, so we have 2x equal to -1. So x is equal to -1/2. Right, so we can make this equal to -1/2, or we just say log base 4 of 1/2 equal to -1/2. Right, we can test 4 to the -1/2. Yeah, it's equal to 1/2. Right, now before we go any further, we have to determine the domain and range of logarithmic function. So earlier we did say that logarithmic function and exponential function are inverse of each other. So I will go back to exponential function. That is in previous section we say for exponential function the domain is all real numbers and the range is positive numbers. Now since they are inverse of each other, we just need to interchange. The domain of the function is the range of the inverse, and the range of the function is the domain of the inverse. So for that, with that we say the domain of the logarithmic function is the range of the inverse function, which is exponential function, all positive numbers, and the range of logarithmic function is the domain of exponential function, which is all real numbers. Right, we'll talk about the graph and others later, but now we just find the domains. Right, so bottom line is the domain of the log of any base, whatever we put here inside the log, the argument of the log have to be positive. Right, so that's what we need. So in this case we have x minus 3, which is the argument of the log, have to be positive because the domain is all positive numbers. So plus 3 on both sides, x greater than 3. So we have the number line, it is greater than 3. Or we just write 3 to infinity. Yeah. So that is the domain of that function. Right. Next. Log base 5 of x squared minus 4. Right, so once again the argument of the log x squared minus 4 must be positive because the domain is all positive numbers. Now x squared minus 4. Right. So it's a little more difficult here. Let's look at the graph of x squared minus 4. We see that it goes through -2 and 2, those are the intercept, or we can write like this. And x squared, so it's open up, so what we have is the graph go through -2 and 2. So the graph so that is the graph. What we want is the graph to be positive, so which means this this portion of the graph is above the x-axis, so we will want that part and we want this part. So the domain for that problem, for this problem, is -infinity to -2, not including, and then 2 to infinity. For those x values, y is positive, so this part is positive, and the argument of the log is positive, so the log is defined. So that's what we have. Right, Next, we have once again the argument of the log x squared plus 5 have to be positive. Now look at the graph. And that is the graph, and we see the graph is above the x-axis. Because of that, we can say the function, x squared plus 5 is greater than 0 for every x. So in this problem, the domain is all real numbers, because it doesn't matter what axis, x squared plus 5 is positive. So that makes this defined. The base of the log, base 3 and base 5 doesn't matter. The domain is whatever the argument is must be positive. So in this case, we just say all real numbers. So those are the domain for the function. Now, properties of the logarithmic functions. The domain, we just say that all positive real numbers, and the range all real numbers. The x-intercept is 1 and 0. If we look at the properties of the exponential function, here, there are no x-intercept in the exponential function, and the y-intercept is 0 and 1. So if we reverse that, we can say for logarithmic function there will be no y-intercept, and the x-intercept is 1 and 0. So as you see, x-intercept 1 and 0, there is no y-intercept. For logarithmic function, for exponential function, there are no x-intercept, and the y-intercept is 0 and 1. So 1, 0 becomes 0 and 1 because we interchange x and y, and the y-intercept interchange give us x-intercept. So from exponential function to logarithmic function, we just interchange x and y, interchange the domain and range, interchange the horizontal, vertical. Yes. So the x-intercept, it will always go to the point 1 and 0, and no y-intercept. We have x equal to 0, or the y-axis is the vertical asymptote. For the base a, that is between 0 and 1, it is decreasing. So this is exactly the same as the exponential function, and this is increasing, exactly the same as for exponential function. So if we look at the graph here, if the base between 0 and 1, the exponential function is decreasing, and we have the logarithmic function also decreasing, because it is symmetric on the line y equal to x. The graph of the function in inverse will be symmetric on the line y equal to x, and that's what we have. Now, if the base is bigger than 1, it is increasing, and the log also the same way. And when the base greater than 1, the graph of the log also is increasing. And the function and the inverse are symmetric on the line y equal to x. Yeah, mirror image. Right, so logarithmic exponential function, if the base bigger than 1, both of them increasing. If the base between 0 and 1, both of them decreasing. Right, now we define other bases. We define the natural log base e of x is ln of x. So the ln means the base is e. Of course, earlier we defined e is the constant number 2.8. Let's give 2.7, 1828, and 1828. I think 45, 90, 45, and so on. Right, so that is a constant, and log base e, log the base of that constant of x, we just need to write ln of x, and log base 10 is the common. This is where I copy and paste and forgot to change. This is called the common log. Yeah. So the common log is base 10 and the natural log is base e. In the calculator you see there's two buttons, ln base e and the log base 10, the common log. Okay, the graph like this. Right, so we'll do more of, we study more properties of the logarithmic functions, but now we look at the first part of logarithmic equation. If we have y equal to log base a of x, then we can interchange that to exponential form. We have x equal to a to the y power. Of course, when we do this, one thing to note that x have to be positive. So we need to watch out for, for this expression that yes, it's just, I should write, this will be much better. Log base a, whatever we put in the log have to be positive. So be mindful with the domain of the function. So in this case, we have to solve for, when we solve for the equation, we need to check the answer. So check the answer. For the domain of logarithms. Right, now let's just solve it. First, log base 5 of 2x minus 4 equal to 3. So we will have the base 5 and we interchange the 3 and the 3x minus 4. So 3 goes here and the 3x minus 5, 2x minus 4 go to the other side. 5 cubed should be 125. And then plus 4 on the other side, and then divide by 3. So I have 129 divided by 3 is 43. So 129 equal to 3x. So x equal to 43. Right. Now, always have to check the logarithmic equation to make sure that the domain is positive. Make sure whatever we put in the log have to be positive. So here we'll check. For x equal to 43. So we have log base 5 of 3 times 43 minus 4 equal to 3. All we need to check is that whatever we put here have to be positive, and 3 times 43 minus 4, it is positive. So yes, that check. So the answer is x equal to 43. Yeah, of course we can check the math too, but what we need to check is the domain. Make sure that whatever we put inside the log, the argument of the log must be positive. Right, next, ln of x plus 2 equal to 3. First of all, ln is the log base e. So we can write log base e, and then we can swap, interchange the base e, and the 3 will go here, and the x plus 2 go the other side. And then subtract 2 to the other side. So if x equal to e cubed minus 2. Right. Now with that we would need to check the answer, because whatever we put in the argument of the log must be positive. Must make the argument positive, I should say that. Right. So we check for e cubed minus 2. We have ln of e cubed minus 2 plus 2. Is that equal to 3? So we will have e cubed minus 2 and then plus 2. So here we have inside the log is positive, so that's good. So that means the answer is good because that makes the function defined. Next, e to the 3x equal to 7. Well, this is different. This is not logarithmic equation. What we can see here is this is exponential equation shown for x. So instead of that, we can swap this to log base e, swap the 7 and the 3x. And log base e of 7, we can write that as ln of 7 because base e is equivalent to ln. And then we can just divide by 3. So we have ln of 7 divided by 3. And of course, when we write like that, this is not logarithmic equation. We don't have to check the answer. But just to make sure ln of 7, it is defined. So that's all we need to. Don't really need to check to make sure that the argument is positive because there's not logarithmic equation. Right, now the next question, how many digits in the 7 to 89? Of course, then you said that easy, right? Yeah, that look like there's 75 or 76, who knows. But let's look at a simple example. Let me ask you this: if we have 1, 2, 3, how many digits is that? It's 2, I mean 3, right? So how do we write this? So that is between 10 cubed, which is 1,000, and that is 10 square, which is 100. Right, so 123 between 10 square and 10 cubed. So that gives us whatever this number is, will give us the 3 digits. Then we can look at something else. I just make 2, 5, 4, 2. Of course, that is between 10,000, right? And 1,000. 10,000 is 10 to the 4th power. And this is between 10 cubed. This will be equal to, sorry. And so we can say whatever the power here, that's why this number will give us 4 digits. And then here we have 7 to the 89. So that is 7 to the power of 89. It is 1.6 something, so we can say this is between 10 to the 76 and 10 to the 75. This is 1.6 times 10 to the 75. So if I rewrite this number as 1.6 times 10 to the 75, it has to be less than, first of all, it is going to be greater than 10 to the 75 because it is 1.6 times that, so it's bigger. But this will be less than if we multiply by 10 times 10 to 75. Of course, 1.6 is less than 10, therefore that number is less than this number. And when we multiply this together, we have 10 to the 76. Because of that, this number has 76 digits. Of course, then when we have something bigger than that, like it is overflown. In that case, we have to try something else. But that will be in the next section. So, but for this problem, so that number has 76 digits. Right, I stop the section here. There will be more properties of logarithmic function in the next section. Thank you for watching.